So hello everyone. Let's solve homework one. So the first problem of this homework is you have to determine the Miller indices for these four planes. Let's start with the first plane. So calculate the to determine the Miller indices, you first have to find the intercepts along intercepts in the x, y, and z axis. So in this case, for in the x direction, the intercept is 2, and a is just a unit here. So and for the y direction, as you can see, this is 1a. Actually, there is a 1 in front of a, so we can write 1, and again, a is the unit, and the z, I mean the z-axis intercept is 2. Okay, so to get the Miller indices, you have to just invert it first. At first, you have to invert it. So let's invert this: 1 divided by 2, 1 divided by 1, and 1 divided by 2. Okay, then we need to make it an integer. To make them integer, we need to multiply these fractions with the LCM, or least common multiple. So least common multiple of the denominators. So what are the denominators here? 2, 1, and 2. So what is the LCM for 2, 1, 2? It's 2. So we need to multiply this with 2. Okay. So what we get? We get 1, 2, 1. Okay. So the Miller indices for this plane would be 1, 2, 1. So for this for plane, you have to express like this, and you also have to find the direction normal to this place. So to express the direction, you have to insert a third bracket and just write the same numbers. Okay, so let's move to sorry, let's move to B. In a similar fashion, we can also do this for B. As you can see that for B, let's find the intercept along in the x, y, and z direction. And in this case, you can see that the plane is actually parallel to the x-axis. So the intercept would be infinity. Okay, because it's actually not intercepting the x-axis. Actually, the plane is not intercepting the x-axis. So we write infinity here as the x-axis intercept, and for y-axis it's 1a, so the intercept would be 1, and in the z for the z-axis it's also 1. And again, you need to invert it. So if we invert, let's invert all of them. One, I mean, yeah. And what are the results? 1 by infinity is 0, 1 by 1 is 1, and 1. So the Miller index, I mean the plane will be the plane can be expressed as 0, 1, 1, and the direction normal to this plane will be the same numbers with this third brackets. Okay, let's move to C. Okay, before that, let me erase something. Okay, so for C, the x-axis intercept is half. Okay, the y-axis intercept is 3, and z-axis intercept is 2. And let's invert them. It will be 2, 1 divided by 3, 1 divided by 2. And we need to find the LCM of the denominators. Here the denominators are 1, 3, and 2. The LCM will be 6. So we have to multiply this with 6. Okay. So if we multiply this with 6, we will get 12, 2, and 3. And this is the plane, and the direction normal to this plane would be the same numbers with just a different bracket. Okay. And let's move to D. Okay. Let's make some space here. Okay. So for D, you can see that the x-axis intercept is 1a. So I will write 1. And the y-axis intercept is -1. Okay. Then the z-axis intercept is 1. So when you write the, sorry, so if you invert it and then if you invert it, it becomes same, and it's already integer. So we are not multiplying with the LCM or something. So in the Miller indices, you can, I mean, to represent this as a plane, you can write like this. So minus can be represented like this. Over the number, you can write a bar. So that's actually minus. And this is the plane expression. And the direction normal to the plane is simply the same numbers with same expression and the third bracket. Yeah. So that's problem number 1. Now let's move to problem number 2. Okay, so let's bring this here. This is the solution. This was the solution. And so you in this case, you have to draw the planes and directions here. As you can see that uh, there are first bracket and third bracket, so both direction and planes are here. You have to draw or sketch the planes and directions. So let's start with A. As you can see that 0, 1, 0. Here is 0, 1, 0. You need to invert it to get the intercept or intercepts. So at first 0, 1, 0, 0 is inverted. If you invert 0, you will get infinity. If you invert 1, you will get 1. And if you invert 0, then you will get again the infinity. So infinity, what does infinity mean? I already explained in the first problem that infinity means the plane will not intercept this particular axis. In this case, it's x-axis. So here, as you can see, the x-axis, I mean the plane is not intercepting the x-axis. You have to draw it parallel to the x-axis actually. And then one is y. So I mean y is equal to 1. I mean the plane will intercept the y-axis at 1. I mean the unit is a, so that's why it's written a here. So it will intercept in y equal to 1a. And as you can see, the third one is also imperative. I mean, the plane will run parallel with the z axis actually. So that's and it will not intercept the axis. So that's how you will draw actually. The next go to B. B is equal to 0, 1, 0. It's a direction. So as you can see, the 0 x equal to 0, and just you have y equal to 1. So it's only in the y direction. It's as simple as that. As you can see, this has been drawn here. So it's directly in the y direction because there is no x. Because x is equal to 0, then z is also equal to 0. So it's going towards the y direction. Okay, let's move to C. C is also a plane. So you have to actually divide these numbers with the LCM of these numbers actually. So what is the LCM of these numbers? 203 it's 6. So you have to divide this by the LCM. So which is 6. So I am dividing this with all this. I'm dividing this with 6 actually. So what I get? I get 1 by 3, 0 and half actually. So as you can see, this is actually the reverse process of problem 1. So that's why we are doing the reverse calculations here to get the planes actually. So yeah, if you can observe, you can realize that it's actually a reverse process of problem 1. Okay, so yep, 1 by 3, 0, 1 by 2, and then you have to reverse it actually. So if you reverse 1 by 3, you will get 3. If you reverse 0, you will get infinity, and if you reverse half, you will get 2. And what does this means? It 3 infinity 2. 3 means the plane will intercept the x at 3, and infinity means it will not intercept the y-axis, and 2 means it will intercept the z-axis at 2 unit actually. So that's what it is drawn here. So the plane is intercepting x at 3, and the unit is a. That's why it's 3a. And the plane will not touch the y-axis, or it will not intercept the y-axis. That's why it's infinity, and it's 2a in the z-axis actually. So let's move to the D, and you can see that I have actually told you in the previous problem that 1 bar means actually -1. Okay, so 1 bar 1 bar it means -1 1 -1. Okay, so you have to go through this process, but these are very simple because they are already actually. What is the process here? The process was to divide these numbers with the LCM, but the LCM of this number is actually 1. So if you divide by 1, you will get the same thing. And if you then you have to invert it, but if you invert them, you will get the same numbers. So these are the numbers actually. After these two processes, the numbers will be the same. That's why no calculation has been shown here. So what is -1? That is the plane will intercept the x-axis at negative -1. As you can see, this is -1. I mean, with the unit, this is -a, and for the y-axis, it's +1. I mean, +1a, and in the and in the z direction, it's -1. I mean, the plane will intercept the z-axis at -1 or -a. Here, a is the unit. So if you connect them, you get the plane actually. So you have to. So what is the main theme of sketching the plane? You have to find the intercepts, and if you find the intercept, just point them. I mean, draw a point on those intercepts and connect them actually. And if it's infinity, then you do not need to intercept the plane with that particular axis. Okay, so let's move to the last one, which is 111 direction. That means, so this is the solution actually. So how do you get this? You have to go to x direction 1 because it's 111. So go to x direction. Let me just draw this for better visualization. Okay, here. Okay. So how do you get the direction? You have to. It was 1 1 1. Sorry about that. Uh, okay, so you have to go towards x direction 1 unit, and then you have to go to y direction 1 unit. Then you have to go to z direction 1 unit. Then you will get a point, right? You will get a point, and just connect this point from the origin. You will get the direction. So instead of 1 1 1, if any other numbers are there, just go in that direction. Okay, suppose 1 2 1 maybe. So let's go towards x direction 1 unit and y direction 2 units. Sorry, 2 units, and in towards the z direction 1 unit. Maybe here. Then connect this final point with the origin, and you will get the direction. Okay. Now let's move to problem number 3. So it's a very similar problem, very similar to problem number 1 actually. So what is the problem here? A body-centered cubic lattice has a lattice constant of 4.83. I mean, this is the lattice constant. I mean, A. This is the value of A. A plane cutting the lattice has intercepts of 9.66 angstrom. Here, as you can see the figure. Okay. So let me draw separately. Maybe this is the x direction. This is the y direction. This is the z direction. So along the so a plane cutting the lattice has intercepts of 9.66 angstrom. So along the x-axis, it's in the x-axis the intercept is 9.66 angstrom. Okay, and in along the y-axis it's 19.32 angstrom, and along the z-axis it's 14.49 angstrom. Okay, so we have to at first we have to actually convert these numbers uh, with respect to A. This is the unit. I mean, you have to convert this, and you need to know how many units are there right here. So the unit is actually 4.83 angstrom. So how many A are there? I mean, how many A is in here actually? So to find that, you have to just divide it by that unit. Then you will get how many units is this actually. So you will get 2. So this is actually 2A. Okay, because A is 4.83 here. So that's how 2 into 4.83 is 9.66. So that's why it's 9.66. So which is actually illustrated here. This is along the x-axis, it's 2A. And along the y-axis, in a similar fashion, you have to just divide this number with the unit, which is 4.83. Here it is showing. If you divide this, you will get 4. And along the z-axis, in a similar fashion, you will have to divide this with 4.83, and you will get 3. So you have got the intercepts, and now the procedure is exactly the same as problem number 1. Uh, sorry, problem number 1, and just it's the intercepts are 2 4 3. Then you have to invert it, which is 1 by 2 1 by 4 1 by 3, and you have to multiply this with the LCM of the denominators 2 4 3, which is 12. So you have to multiply this with 12, and you will get 6 3 4, and this is the plane. I mean the Miller indices, and yeah, so that's it. That's the solution actually. So let's move to problem number 4. So in this question, you have to determine the surface density of atoms for silicon on these planes, these 3 planes, and the lattice constant is given 5.43 angstrom. So what we need to do, or we need to see what atoms are there in these planes. So let's let's start with 100 plane. So I have opened a website here. I will post the link of this website in the canvas. This is an interactive 3D crystal of silicon here. So as you can see, this is the yellow or orange plane is the 100 plane. Let's see which atoms are on these plates. As you can see, this is one corner atom, this is another, this is another, and this is another. So four corner atoms, and there is another atom right here in the middle. So this picture comes from this plane actually. So as you can see, there are four atoms in four corners, and uh, there is another atom in the middle. So this is for 100 plane. And let's move to the next plane, which is 110 plane. So in this 3D picture, this green plane is the 110 plane, and as you can see that there are many atoms inside this plane that actually let's see, let's count it. So we have one corner atom right here, then in the middle right here the blue atom, and then there is another atom. So there are three atoms at the top layer. As you can see in this picture, there are three atoms right there. And let's move below. As you can see that there are two atoms in this middle plane, not middle actually, it's slightly above the middle. So these two atoms are these two atoms in this picture actually. Now let's move below at the lower layer. As you can see, there are three atoms, one in the corner, the other is also in the corner, and there is one in the middle. So that's what has been drawn right here actually. And this is for 110 plane. And now let's move to the last plane, which is 111 plane. As you can see, the uh, violet or purple color plane is the uh, 111 plane. And as you can see that we have one atom right here and another one right here and one right here. And as you can see, uh, these three atoms are also are on the middle of the side of this triangle actually. So we have three atoms uh, right in the middle of the sides and three atoms in the three corners of the triangle. And I think that's it. There are no more atoms in this plane. So these three corner atoms and these three atoms which are in the middle of the sides. So this is the one plane, and actually this picture comes from right here. So yeah, this is an interactive 3D crystal. I'll post the link in the canvas of this website. It's helpful actually in the planes. So for 100 plane, as you can see, the corner atom is not fully inside the uh, plane actually. Let me take a screenshot of these pictures. Paste it right here. So okay, so let's focus on 100 plane. So let me change the color. Yeah. So this is basically the 100 plane. So as you can see, this whole atom is not inside the 100 plane. Just only 1/4 of this atom is inside the plane. So we will not take the whole atom in the count. So we will take 1/4 of this atom is inside the plane. So how many we have this kind of atoms? We have four into 1/4. I mean, there are four atoms like this. So the atom count will be like 4 divided by 1/4. That is 1. And we have a full atom uh, here, which we will add. So the number of atom we have in this 100 plane is 2. And to get the surface density, we need to just divide this number by the area of this plane actually, which is, as you can see, this is a square. So the area will be a square. So that's what actually written here, 2 divided by a square. So this is the atomic density or surface density of this 100 plane. So you have to put 5.43 angstrom
in this A and then calculate the density actually. Similarly, let's move to the 110 plane. So let's draw it here. So let's zoom a little bit. Let me draw the plane here. So what will be the case for these four atoms? As you can see, only 1/4 of these atoms are inside this 110 plane. So we have four of these and 1/4 of these atoms are inside the plane. So we are getting this. And then move to these atoms. As you can see that half of these atoms are inside the plane. So we have two of this kind of atoms and half of these atoms are inside the plane. So 2 multiplied by half. And we have other atoms as well, these two atoms. So these two atoms are fully inside this plane. So we can write 2 into 1. I'm writing 1 because full atom surface is in this plane actually. So what we get, this is 1 and this is also 1, 1 and 2, this is 4. So that's what written here, 4 divided by the number of atoms is 4 here. And the area, let's move to the area. So what is the area of this? As you can see, one side of this, this is a rectangle. One side of this rectangle is A. This is A actually, and this is root 2A. How did we get root 2A? Because let me go to the area. Okay, so as you can see, this side is A, and this side is also A. So according to Pythagorean theorem, what will be the length of this dimension or of this triangle? It should be root over A square plus A square, right? So uh, that is root 2A. If you calculate this, you will get root 2A. So that is the area, root 2A or A root 2 is the length of this side of the rectangle. I mean, yeah, this root 2A. This is one side of the rectangle and the other side of the rectangle is A. So if you multiply this 2 and you will get the area. So yeah, so that's how you get root 2 A square. So the number of atoms in this 110 plane was 4 and the area was root 2 A square. And you put A equal to 5.43 angstrom and you will get this the result actually. Then let's sorry, move to the third plane, which is 111 plane. So we have already discussed that how this figure comes. Okay, so let's calculate the number of atoms in this plane. So easy things first. So these let's consider these atoms. As you can see, let me draw the plane correctly. So this is actually the 111 plane. And as you can see, for these three atoms, half of the atoms are inside this plane. So we can get the number from this. So 3 atoms and half of them are inside the plane. And we have other atoms here. So this one, and this one. So as you can see that 1/6 of the atom inside the plane. How? Let me give you some details. Enlarge the picture. Okay, so okay, so you realize that this is actually a equilateral triangle. So uh, each angle should be 60-degree, right? So this is actually, this color is not visible. So let me move to a new color. This is 60-degree. So uh, let me draw a circle. This is 60 degrees. So from the full atom, you are basically taking this portion, right? Uh, look at this. Look at this atom. So I have just drawn it bigger to better understand. So yeah, so you are getting this portion from the atom. So and this is 60-degree, and you know that the whole thing is 360-degree. So this portion, how much is this portion of the whole circle? So you can get that by just simply dividing 60-degree uh, by just dividing 360 degree with 60 degrees. So you will get 6 maybe. So this implies that this triangle, or not, this is not a triangle, this pi, actually this portion of the circle takes 1/6 of the full atom. Okay, so that's what we got. 1/6 of the atom is inside the plane of for this for this plane actually. So how many of these kind of atoms are there inside this plane? So we let us count this one, and this one. So three. Okay. So we have three of these types of atoms actually, where we get 1/6 of the atom inside the plane. So we have got three atoms where 1/6 of the atoms are inside the is inside the I mean 1 1 1 plane. So let's add that, and you will get the number. Maybe it should be 2, right? Okay, that's what written here. As you can see that the number of atoms in 1 1 1 plane, which is 2, and the area you should if to get that surface density, you need to divide the number of atoms by the area. So let us get the area of this uh, structure, maybe of this plane. So to here, the area is written here. So we will get the idea of the area from this picture. So here is the picture, and we already have shown that this is a root 2. In the case of 1 1 0 plane, we have already shown that this is a root 2. The length of this dimension is a root 2. And now let's move. This is a equilateral triangle, so the formula of the area should be half base into height. So we have got the base already, which is a root 2. So half base is a root 2. So what should be the height of this triangle? So let me draw it first, then calculate. Um, let's decorate. So actually this will be the height of this triangle. So how will we calculate that? Okay. So to calculate that, maybe we should take another triangle inside this triangle, maybe inside the structure. So let's take another color. I'm considering this triangle. Look, this atom is the 0, 0, 0 atom. I mean, the coordinate of this atom is 0, 0, 0. Yeah, so and this is the atom. Oh, the coordinate of this atom is actually 0, 0, 1. Okay, so let's bring that triangle outside to better visualize. So what is this dimension? It's actually the A. I mean, uh, yeah, this is A. And what is this? Half of the diagonal of this square, actually. The base square. Look at the base. Look at the square, which is in the base. And as you can see, this is one diagonal of this base, and we need to calculate the length of this half diagonal. So the full diagonal we have already calculated, which is a root 2, uh, which is for the blue line. But in the case of this red diagonal, it's also a root 2 because it's a square, right? So this is the diagonal, and half of the diagonal should be a root 2 divided by 2, right? So this is the base of the triangle, actually. The base of this triangle that we are calculating. Okay, so according to Pythagoras, what would be the length of this dimension? It will be just a the length of this side square plus the length of this side square. Okay, it's 2 actually. So let me calculate that. So basically, if you calculate, it should be a square plus a square divided by 2. So it should be 3a square divided by 2, and ultimately root 3 divided by root 2a. Okay. Okay, so this is what is this? This is only let me name it A, and this is the point B. So this is the length of AB, which is our what is this? Which is actually the height of our main triangle that we are calculating actually. So we have calculated this the length of the height of this triangle of 1, 1, 1 plane, I mean. Okay, so let's plug in this in the formula. So it would be root 3 divided by root 2 into A. Okay. So ultimately, it comes down. So ultimately, this should be the result of the area of the 1, 1, 1 plane, which is root 3 divided by 2a square, which is actually shown right here. Is the calculation. And yeah, so root 3 divided by 2a square. To get the surface density, you need to just divide this area of the plane, and you will get the surface density for 1, 1, 1 plane. So yeah, that's how you calculate the surface density. Thank you.
So let's start problem 5. Okay, so the question is the uncertainty in position is 12 angstroms. I mean, this is delta x uncertainty in position. Okay, for a particle of mass is given, I mean, the m is given. So the first question is determine the minimum uncertainty in momentum and velocity of the particle. So let's first thing first, momentum. So we need to get momentum, uncertainty in momentum. Okay, so we need to get delta p, right? So relating to these two, we have an equation which is delta x uncertainty principle, Heisenberg uncertainty principle. Delta x multiples delta p is greater than equal to h cut. Okay, so we need to find delta p. Let's rearrange the equation. So delta p is greater than or equal to h cut divided by delta x. Okay, let me clear up things underneath. Okay, so yeah, so you have to find the minimum uncertainty in momentum. Okay, minimum. So what could be the minimum of delta p here in this equation? This is an actually inequality. So in this inequality, what is the minimum value of delta p here actually? We will get the minimum delta p is when we just convert this inequality equation to equal to, because what is the minimum value of delta p when this is equal to h cut divided by delta x? Delta p can be bigger, right? But what is the minimum value when this is equal, right? So we can write delta p minimum equal to h cut delta x. Okay, so what is h cut? H cut is simply h divided by 2, where h is the Planck's constant, right? H is the Planck's constant. The value, the value of h is 6.63 into 10 to the power minus 34 in SI unit. Okay, and you have to insert the delta x value here, which is 12 angstrom. If you want to measure it or calculate it using SI unit, you have to convert 1 angstrom to 10 to the power minus 10 meter. Okay, so that's how you will get the delta p minimum. And the velocity, what is the velocity? We have m, right? And we have delta p. So how will we get the velocity? There is a relation between m and delta. I mean p and m. P is momentum, right? So what is the formula of p? I mean momentum is simply mass times velocity, right? So delta p minimum will be let's write the mother equation first. P equal to mv. We know that. So in our this special case, we are writing delta p minimum because we have delta p minimum and we have m, and we have to find what? We have to find the determine the minimum uncertainty in velocity. Okay, so we have to find delta v minimum. So actually this equations comes from this equation. Okay, so now it's easy, right? Because we have m and we have delta v minimum, then we just need to rearrange the equation to get delta v minimum, which is delta p minimum divided by m. M is already given in the question, and delta p minimum you will get this from yeah, we have already calculated this from this equation. Now let's move to the part b. Part b is simply the same, just you need to change the value of m and repeat all these calculations. Okay, so that's problem number 5. Let's move to problem number 6. In problem number 6, the electron's energy is measured with an uncertainty no greater than delta, sorry, 0.8 electron volt. And no greater than, what does it mean? It's the maximum value, right? So delta E, I mean the uncertainty in energy. So delta E max is given, which is 0.8 electron volt. Determine the minimum uncertainty in the time. I mean delta T minimum is required. You have to find this value, okay? In the time which over which the measurement is made, whatever. So we have an equation relating these two, which is delta E times delta T is greater than equal to h cut. I mean h cut, you can write h cut, just h cut. Or h cut divided by 2, whatever. Okay, so then just rearrange the equation to get the delta T minimum. I mean, not the equation, this is inequality. So we need to find the minimum, right? Delta T minimum. So this is the delta T value. Delta T can be equal to this value or can be greater than this. So what is the minimum value? The minimum value is this value, but delta T can be greater than this, but this is the minimum value. So we can write delta T minimum is equal to h cut divided by 2 delta E. Delta E is already given in the equation, so you have to plug it in, and h cut you can write h cut equal to h by 2. H here is the Planck's constant. So that's how you solve problem number 6. Let's move to the next problem. So this is more or less same question, actually, this similar question, I'll say. The uncertainty in the position of an electron is no greater than 1.5 angstrom. I mean, the uncertainty in position is delta x is no more than, I mean, this is the maximum value. Okay, determine the minimum uncertainty in its momentum. So delta p minimum is needed. This is almost same as the previous problems. So we have delta x times delta p is greater than h got divided by 2, and we need delta p is greater than h got divided by 2 delta x. And in a similar fashion, delta p delta p is can be greater than this value, but what is the minimum value of delta p? Equal to this value actually. I mean the delta p minimum is equal to h got divided by 2 delta x. Delta p can be greater than this h got divided by 2 delta x, but the minimum it can be is h got divided by 2 delta x itself actually. So you have h got delta x. You have to just plug it in to calculate this value. Okay, now let's move to problem number 8. So this is problem number 8. The de Broglie wavelength of an electron is 85 angstrom. So wavelength, I mean lambda is given. Determine the electron energy, I mean E, energy, then momentum, then velocity. All these three needs to be calculated. So this is the de Broglie wavelength. So we can apply the formula, de Broglie formula. So what is the de Broglie formula? It's lambda equal to h divided by p. Okay. And here from this h is a constant, and from this you can easily calculate p equal to h divided by lambda. H is a constant, Planck's constant, and lambda is already given 85 angstrom. Okay, then we have got our p, and then from p we can calculate the v, because there is a relation between p and v, which is p equal to mv. Uh, p equal to mv. So we have p already calculated from the first part of this calculation, and we have to calculate the v. And this is electron, we know the mass of electron, which is 9.11 into 10 to the power minus 31. So if we plug them in, then we will get the value of v. Okay. Okay. So next, let's move to okay. We have got p, we have got v. Then we have to calculate the value of e. We know the formula of energy, or E, which is half of mv squared in this case. So we know m, the mass of electron, which is 9.11 into 10 to the power minus 31 kg, and we have already calculated the v from the second part of this calculation, and then we will get the value of E. Okay, let's move to the next problem. So in this problem 9, an electron is moving with a velocity v. So v is given. Determine the electron energy. I mean E has to be calculated. Energy, momentum, and de Broglie wavelength. I mean lambda. So as this is an electron, so we also know the value of m. I mean the mass of the electron is 9.11 into 10 to the minus 31 kg. So you have to calculate these three values. So from m and v, we already know the I mean the energy. Here it is written, energy is equal to half of mv square, and m is equal to 9.11 into 10 to the minus 31 kg, and v is already given. And keep in mind that you have to convert this value. The velocity is given in centimeter per second. You have to convert it to meter per second to get the SI unit. Okay, and yeah, so that's how you will get the energy. And for the momentum, you know the formula, p equal to mv, where m is the electron's mass, and v is given 80 to 10 to the 5 centimeter per second. You have to convert it to meter per second. Okay, and then de Broglie wavelength, we know the formula, p equal to h divided by lambda, and then you have to find the lambda equal to h divided by p. You have already calculated this from here, and h is the Planck's constant. So that's how you will calculate. Let's move to the last problem. A car of mass 2000 kg, I mean the m is given, is moving with a velocity 60 mile per hour. V is given, calculated de Broglie wavelength, I mean lambda. So we know that lambda equal to h divided by p, p equal to, and p equal to mv. So h is known, it's a constant, and m is already given, which is 2000 kg, and v is 60 mile per hour. You need to convert this 60 mile per hour to meter per second to get SI unit, and you have to plug it in this equation, and you will get a lambda or de Broglie wavelength. So this is it. Thank you so much.